The other algorithm is the positional weight method for balancing a line. So similar to the most following, the maximum time allowed at each workstation is equal to the cycle time. We start off by computing the positional weight of every task. What is positional weight? The positional weight is the sum of the task time and the times of all the tasks that follows after it in the precedence diagram. So that's the positional weight. So first, we create a table for each task. We're gonna compute the positional weight and we're gonna fill that out. We know what positional weight each task has. After that, we're going to start with workstation number one, and the time available is equal to the cycle time. And then we identify tasks that are eligible for assigning to workstation one based on the precedence diagram or precedence relationship. So we create a list of eligible tasks. Next, we're going to eliminate tasks from the eligible list that will not fit into the station's remaining available time. That would produce will fit list. And the next step, step 5, is to assign the task from the will fit list that would have the greatest positional weight. So if you have different options, different tasks to assign, the task that has the greatest positional weight is going to be assigned first. And then reduce the available time at the workstation. You're going to update the workstation remaining time. And the step 6 is if all tasks are assigned, we're going to stop. If there is sufficient time available at a workstation, we're going to go to the next eligible list of tasks. Otherwise, we're going to go to the next workstation. So let's see actually how this would work on an example. We're going to work on the same example as we worked on using the most following method, this time with the greatest positional weight method. So please pause and try to work on this example. Try to balance the line for this example using the greatest positional weight method. And after you're done, come back to see the solution. We start off with computing the positional weight for each task. So we have created this table here. The first column shows the task A, task B, C, D, and E. And the next column is the positional weight. So let's see how we can actually compute the positional weight for task A. So for task A, we're going to add up and sum up the processing time of task A and what follows task A. So that's 0.1 for task A. Task B follows task A, and the processing time is 1. Task D follows task B, and the processing time is 0.5. And task E follows task D, so the processing time is 0.2. So that's 0.1 plus 1, 0.1 plus 1 plus 0.5 plus 0.2. And that is equal to 1.8. Similarly, we can compute the processing time for B, C, D, and E to create this table. So that's the first step, to compute the positional weight for each task. Now we can start off with the algorithm. All right, so let's start the algorithm. We already computed the number of workstation when we were working on this example for the most following method. So the number of workstation here is again similar, 3 workstation. We have the positional weight computed from the table that we had before. So let's go ahead and start the algorithm. So the algorithm starts with workstation 1. We have 1 minute, which is the cycle time for this algorithm. This is the workstation 1. And the eligible tasks are task A and C. This is the precedence relationship, A and C. Next column is whether they fit or not. That means that we have enough time remaining in workstation 1 for task A and C. Well, yeah, both of them actually, each of them would actually fit A and C. Now we're going to assign task between A and C, which one has the most, the highest or the greatest positional weight? A is 1.8 and C is 1.4. So we're going to assign task A. Task A. And task A is going to require 1.1 minute. 0.1 minute. So we're going to update the time. That's 1 minute minus 0.1, that's 0.9 minutes. So we're going to end up with 0.9 minutes here. And we already assigned task A. Okay, so what are the eligible tasks now? The eligible tasks are task C and task B. So tasks C and B. Will each of these fit? Would task C, yes, would fit because 0.7 is less than 0.9, so it would fit. But task B would not fit because it requires 1 minute and we only have 0.9 minutes. So the only task that would fit here is task C. And we're going to assign it. We're going to assign it, and the time remaining would be 0.9 minus 0.7 for task C. So that's 0.2 minutes. Okay, so we end up with 0.2 minutes left here. We assign task C. So the only eligible task here is task B. Does it fit? No, it doesn't fit. So we're going to close workstation 1, and the idle time is 0.2 minutes. We're going to open workstation 2, and what are the eligible tasks? The eligible task is, first of all, we have 1 minute at workstation 1. The eligible task is task B, and it does fit because it requires 1 minute, and we're going to assign it, and we're going to update the time. The time would be 1 minus 1, 0. So we're going to end up with 0 minutes here. So we're going to have 0 minutes, and we're going to close the workstation 2 as well. And we're going to go with workstation 3. So task 2 was B as was assigned. We have 3 minutes. We have 1 minute at workstation 3. And the eligible task is task D. What does it fit? Yeah, it's 0.5 minutes. It does fit. And since it is just one task, we're going to assign it. And we're going to update the time. So that would be 1 minus 0.5, which is 0.5. So we are going to end up with 0.5 minutes left. And we have already assigned task D here. So the only task that remains is task E. Does it fit? Yes, 0.2 minutes it requires for task E, and we have 0.5 minutes here. So it does actually fit. So we're going to assign it. Task E. And we're going to end up with 0.3 minutes. And since we don't have any other task, we're going to close the workstation 3 as well, and we're going to end up with 0.3 minutes as idle time, a total of 0.5 minutes. So this is a more clear version of the solution that we have. Everything is typed out and clear for you to see. So we assign task A and C to workstation 1, we assign task B to workstation 2, and we assign task D and E to workstation 3. Next example. Suppose that we want to make 40 units of our product each day. So this is our output rate, 48 units per day. And that we can manufacture the product in 1 8-hour shift. So every day we have 8-hour shifts. And that means that our operating time is 480 minutes per day. 8 hour multiplied by 60 minutes, so that's 480 minutes per day. Use the positional weight method to balance all the tasks for the following example. This is the example. We have 6 tasks here, as you see. The precedence diagram is shown here, and you also have the processing time of each task. So use the positional weight method to balance these tasks, this line. So please pause. Try to first you need to find the cycle time. After that cycle time, compute the theoretical minimum number of workstation, and then use the positional weight by computing the positional weight table, and then use the algorithm to assign the task to workstations. After you're done, come back to see the solution. First, we need to compute the cycle time. So cycle time is equal to the total available time, which is 480 minutes per day. This is minutes, 400 minutes a day, divided by the output rate. So the output rate is 48 units per day. So this is equal to 10 minutes. So the cycle time is 10 minutes. Next, we need to find the positional weight. So for the positional weight, and these are the tasks. For task A, B, C, D, E, and F. So task A, the positional weight is 4 minutes plus 5 minutes plus 1 minute plus 7 minutes plus 2 minutes plus 6 minutes, which is a total of 25 minutes. For task B, that's a total of 5 minutes plus 2 minutes plus 6. So that's 13. For task C, we have 1 minute here and 7 minutes here, so that's 8. For task D, that's 2 minutes plus 6 minutes, so that's 8. That's 8 as well. Task E, it's only 7 minutes. 7 minutes. And task F is 6 minutes. 6 minutes. So cycle time 10 minutes, and these are the weights, positional weights for each task. Now let's go ahead and start the algorithm. We start with workstation 1. The time remaining at workstation 1 is the cycle time, which is 10 minutes. And the eligible task here is only task A. We need to start with task A. There's no other task that we can start with. So task A, does it fit? Yes, it requires 4 minutes and we have 10 minutes, so it does actually fit. And we're going to assign it because it's just one task. The time remaining would be 10 minutes here minus 4 minutes for task A, and that would give us 6 minutes left. So we end up with 6 minutes. We assign task A, so now we have two choices here, B and C. So the eligible tasks are B and C. Do they fit? We have 6 minutes, and task B would require 5 minutes. Task C would require 1 minute. So yes, A, B, and C both actually they fit. Each would they fit. So B and C. So we have two options. Which one should we choose? Well, the positional weight for task B is 13. For C is 8. So we're gonna assign B, which is it has a greater positional weight. So we're gonna assign B, and it would require 5 minutes. So our total time remaining would be 6 minus 5, which is 1 minute. So we have 1 minute left here. We assign task B. Now we have two eligible tasks, task C and task D. C and D. Do they fit? Well, task C does fit, but task D does not because it would require 2 minutes. So the only task that we can assign is task C. And since it's just one task, we're going to assign it. And we're going to end up with 0 minutes left. So we're going to close workstation 1. So 0 minute idle time. We're going to start with workstation 2 now. it has 10 minutes cycle time at disposal, and the eligible tasks are, we already have assigned task A, B, and C, so now D and E are eligible. D and E. Do they fit? D and E both actually do, they actually fit. So which one should we assign? Task D has 8 minutes, 8 positional weight, and task E is 7. So 8 is greater than 7. That means that we're going to assign task D. So task D. And task D would require 2 minutes. So 10 minus 2 minutes, we're going to end up with 8 minutes left here. 8 minutes. So we have assigned task A, B, C, and D. And now we have 8 minutes at workstation 2. What are the eligible tasks? Task E and task F are eligible. Task E and F. Do they fit? Well, task, yes, both of them actually fit. So E and F. Which one should we assign? E is 7, the positional weight, for F is 6. So F is, E has a higher, greater positional weight. So we're going to assign E. And it would require 7 minutes. So the time would be, remaining time would be 8 minus 7, which is 1 minute. Since task F would require 6 minutes, we're going to actually end up closing this workstation with 1 minute idle time. So we assigned A, B, C, D, and E. So we only have one task left. We're going to open workstation 3, and it has 10 minutes left remaining time. The eligible task, the only task left is task F, and it does actually fit, and we're going to assign it, and we're going to end up with 10 minus 6, 4 minutes. So 4 minutes, since we don't have any other task, we're going to close workstation 3 as well, and we're going to end up with 4 plus 5, 5 minutes. We're going to have 5 minutes of idle time with this assignment. Right, so this is a more clear and typed out version of the solution. As you see here, we have a total of 5 minutes idle time, and we have assigned all the tasks. We have assigned task A, B, and C in workstation 1. We have assigned task D and E workstation 2, and we have assigned task F to workstation 3. So a total of 3 workstation. The total time for workstation 1 is 10 minutes. Workstation 2 is 9 minutes, and workstation 3 is 6 minutes. So there is a little bit of disparity or difference between the workstation utilization, as you see here. Now we can actually compute the utilization or the efficiency for this assignment. So this is the line balancing output, the result of line balancing using the positional weight method. We would have to put assign task A, B, and C to workstation 1, task D and E workstation 2, and task F to workstation 3. So let's now compute the using the percentage idle time and also the efficiency measure to compute the output or the effectiveness of this method for this example that we did. So the percentage of idle time, for this example is equal to the total idle time that we have. So total idle time divided by the number of workstation multiplied by the cycle time. So that's the number of workstation multiplied by cycle time. And that's equal to the total idle time was 5 minutes, and we have 3 workstations multiplied by 10 minutes cycle time. So that's 5 divided by 30, which is 16.6%. 16.6%. To compute the efficiency, um, efficiency is, so unlike the idle time, which is the smaller the better, efficiency must be maximized. So efficiency is just 100% minus the idle time, percentage of idle time, which is 16.6%, which is 83.3%. So the idle time, the percentage of idle time is 16.6%, and the efficiency is 83.3%.